Hello friends, so welcome to the third lecture of this unit, and in this lecture I am going to introduce a special type of function called gamma function. This function is related to the improper integral and having plenty of applications in multiple integral. So that is why I put this particular topic here. Many multiple integral can be solved directly in terms of gamma function. So let us look at a bit history of this function. So the gamma function was first introduced by the Swiss mathematician Leonhard Euler in 1730 in his goal to generalize the factorial function to the non-integer value. As we know that factorial function is defined only for integers, and how to generalize it for non-integer values, from that concept the development of gamma function was started. Since this function was quite important, so it was later studied by other eminent mathematicians. The gamma function belongs to the category of the special transcendental function due to the involvement of exponential term in its definition. Furthermore, it is having applications in various areas as asymptotic series, definite integration, hypergeometric series, number theory and many more. So let us start with this lecture with the definition of gamma function. So in 1730 Euler defined the gamma function with the help of an improper integral, and the definition was something like this: let x be a positive number, then gamma of x. So this symbol stands for gamma function. So then gamma of x is defined as gamma x equals to integral over 0 to 1 minus log t raised to power x minus 1 dt. So this was the definition given by Euler in 1730. However, rarely we find this definition in textbook. So if I put or change the variable as u equals to minus log t, here log is defined with a base exponential, means natural log. So what I can write, t equals to e raised to power minus u. So I have taken minus this side and then taken the exponential on both sides, and this gives dt equals to minus e raised to power minus u du. So if I put it here, then gamma x will be 0 to infinity, and then u raised to power x minus 1 into e raised to power minus u. It is coming from here, limit has been changed from 0 to 1 will become infinity to 0, and since I am having a minus here, so it will become 0 to infinity, and then finally du. So this is the most popular definition of gamma function, which we used to see very frequently in textbooks related to this topic, and this is defined for positive x. Now with this definition we will see some important property of gamma function. So the definition which we have just seen is like gamma x equals to 0 to infinity u raised to power x minus 1 into e raised to power minus u du, and it is when x is a positive number. Now, if I want to find out the value of gamma 1, so gamma 1 means here I need to put x equals to 1. So, 0 to infinity u raised to power 1 minus 1 will become 0. So, u raised to power 0 will be 1, and then e raised to power minus du, and this equals to 1. So, hence gamma 1 equals to 1. If I need to calculate gamma x plus 1, so in this definition I will replace x by x plus 1. So, it will become u raised to power x plus 1 minus 1 into e raised to power minus u du. So, basically 1 will be cancelled out with this one. So, it becomes u raised to power x into e raised to power minus u du. Now, if I do this integration by parts, I assume it as my first function, this one as my second function. So, this will be first function as such, integration of second. So, it will become minus e raised to power minus u, and this will be having 0 to infinity minus integral over 0 to infinity the differentiation of the first function. So, u raised to power x can be written as x u raised to power x minus 1, and this will be again integration of second. So, minus e raised to power minus u. So, with this minus, this will become plus into e raised to power minus u du. Now, just see this term, when u is 0, this term will become 0, because this will be 1 and this will be 0. So, this is 0. When u is infinity, so it is something limit u tending to infinity, I can write it u raised to power x upon e raised to power minus u, sorry, minus u is here. So, I can take it down. So, e raised to power u. Now, it is the form of infinity upon infinity. So, using L'Hospital, it will become x u raised to power x minus 1 upon e raised to power u. Doing it, finally, I will be having limit u tending to infinity. Here I will be having x into x minus 1, x minus 2 up to 2 into 1 like this, and in the denominator I will be having e raised to power u. Here this will be some finite number, however, this will be infinity. So, I can write it as 0, because growth of exponential function will be more than the function given in numerator. So, hence this term is 0. So, I can write it, I can take this x out. So, x 0 to infinity u raised to power x minus 1 e raised to power minus u du. Now, this is quite familiar to us, this is gamma x. So, it will become x gamma x. So, basically we ended up as the second property that gamma x plus 1 equals to x gamma x. So, from this definition we have obtained two important properties of gamma function. One is gamma 1 equals to 1, another one is gamma x plus 1 equals to x gamma x. So, together with this definition, over the time several other definitions were proposed for this particular function. In 1922, Bohr and Mulroop proposed this particular definition. So, definition is like this: there is a unique function f from the 0 to infinity to 0 to infinity, such as log of f x is convex and f 1 equals to 1 and f of x plus 1 equals to x times f of x. So, if we look in these two particular statements, these are quite similar, which we have just proved, that gamma of 1 equals to 1 and gamma of x plus 1 equals to x gamma x. And please note that it is defined for positive x. It is also possible to extend this definition to negative values, because whatever we have taken so far, we have taken only for positive x. So, we know that gamma of x plus 1 equals to x times gamma x. So, I can write that particular property in this fashion. So, gamma x equals to gamma x plus 1 upon x, and this is definition, and this gives the definition of gamma function for negative numbers except the negative integers like -1, -2, etc. For example, if I want to find out gamma of -12, so here if I put -12, it will become -12 plus 1. So, gamma half in the numerator, and the denominator it will become -12. So, it will become gamma -12 equals to -2 times gamma half. Reiteration of these identities allow to define the gamma function on the whole real axis, as I told you, except on the negative integers and 0. So, this particular plot gives the graph of gamma function. So, here you can see we have just plotted it from -4 to 4. So, if we talk about positive x, the function will be like this. So, it is decreasing up to 1, a bit more than 1, and then it is increasing. Okay. So, it is something convex type of thing. For the negative x, what we are having between 0 to -1, as I told you, if we look at the value gamma -12, it will be -2 times gamma half. Gamma half will be something positive quantity. So, -2 times some positive quantity. So, it will become negative quantity. So, between 0 to -1, the value of gamma function will be always negative. If we talk between -1 to -2, so suppose we need to find out gamma -3/2. So, I need to find out gamma -3/2. So, how can I write this gamma -3/2? So, this can be written as I told you, gamma x plus 1 equals to x gamma x. So, this -3/2 times -3/2 will be gamma -3/2 plus 1. So, this value will be gamma -12. So, hence gamma -3/2 will be -2/3 times gamma -12. This is a negative quantity. As I told you, gamma -12 will be a negative number. So, negative into negative will become a positive number, or basically it will become -2/3 -2 into gamma half. So, 4/3 into gamma half. Since gamma half is a positive quantity, so it will be positive. So, all the value of gamma function for all the values between -1 to -2 will be a positive quantity. So, again from minus 2 to minus 3 it will be negative, minus 3 to minus 4 it will be positive. So, it will alternating in this way. And please again note that the gamma function is not defined for negative integers. The another definition for gamma function given by Euler in 1729 and Gauss in 1811 is like that. So, this definition is based on the product of infinite terms. So, let x is a positive number, then define gamma px in this fashion, factorial p into p raised to power x upon x into x plus 1 up to x plus p. So, this can be written as in this way. Then gamma x will be limit p tending to infinity gamma px. For example, if we want to find out the value of gamma 1 from this definition, so gamma p1 will be, just put x equals to 1 here. So, it will become p upon p plus 1, and gamma 1 will be limit p tending to infinity p upon p plus 1, which is obviously 1. Similarly, gamma px plus 1 equals to p upon p plus x plus 1 into x times gamma px. In limiting case, this value will become 1, gamma 1 is 1. So, gamma x plus 1 will become x gamma x. So, again this definition drives the two important properties which we have obtained using the definition given on the first slide of this lecture. Now, we will evaluate some important values. First of all, we will find out the value of gamma half. So, I will take it as an example. So, find gamma half. So, it is an interesting problem that finding the value of gamma half. So, we know that gamma half will be by the definition something u raised to power half minus 1 e raised to power minus u du. This becomes 0 to infinity u raised to power minus half e raised to power minus u du. If I substitute u equals to t square, so let u equals to t square, then du will become 2t dt. So, after substituting this integral will be 0 to infinity and then 2 times. So, t is basically square root u. So, square root u will cancel this u raised to power minus half. So, it will become e raised to power minus t square dt. So, basically what I am writing? I am writing gamma half equals to 0 to infinity e raised to power minus u square du. Just that t I have written in terms of u again. Also, I can define gamma half as 2 times 0 to infinity. If I take v instead of u, e raised to power minus v square dv. If I multiply these two equations, I will be having gamma half whole square in the left hand side, that is gamma half into gamma half. In the right hand side, I will be having 4 times 2 into 2 4, 0 to infinity e raised to power minus u square du, 0 to infinity e raised to power minus v square dv. By the Fubini theorem, I can write, since the limits are constant, I can write it the product of these two definite integrals as a double integral. So, it will be 4 times 0 to infinity e raised to power minus u square into e raised to power minus v square. So, it will become e raised to power minus u square plus v square du dV. Now, I need to solve this particular integral, that is the double integral. What I will do? I will change the variable in polar coordinates. So, what I am doing? Put u equals to r cos theta and v equals to r sin theta. So, from here the integral will become 0 to infinity, that is gamma half square 0 to infinity, for I am having already here e raised to power minus r square, and as you know du dv will become r dr d theta. Again, for first I will solve this integral. So, for solving this integral I will put r square equals to z. So, what I will be having? 2r dr equals to dz, and sorry, after putting this, limit will change, limit will be in now according to polar coordinates. So, as you know it is 0 to infinity and 0 to infinity. So, region is first quadrant. So, first quadrant means r will move from 0 to infinity and theta will be 0 to pi by 2. So, this by this substitution it will become 2 0 to pi by 2, because I have taken this 2 inside 2r dr. So, 2r dr will be dz. So, zero to infinity e raised to power minus z dz, 2 0 to pi by 2, and this will come out as 1, and sorry d theta is also here. So, d theta. Now, 2 into pi by 2 will come out pi. So, what I got here? I got gamma half square equals to pi. So, it will give me the value of gamma half. So, gamma half square is 5. So, from here I will get gamma half equals to root pi, and which is one of the important result in gamma function. Okay, so just now we have seen that gamma half equals to root pi. Based on this result we can solve many other integral which is not possible to solve without the knowledge of gamma function. So, one of them, let us take 0 to infinity e raised to power minus u square du. So, if we do not have the knowledge of gamma function, for solving this integral we need a u here just before e, but we do not have it here. So, we cannot make any proper substitution here. However, since we have the knowledge of gamma function, so we use the property, or I will say the definition of gamma function here. So, if I assume let u square equals to t, then I can write du equals to 1 by 2 root t dt. So, after making this substitution, this integral I can be written as 1 by 2 0 to infinity t raised to power minus half. So, t raised to power minus half can be written as t raised to power half minus 1 and then e raised to power minus t, because earlier it was u square. So, now just in place of u square I have written t dt. If you see this definition, this is gamma half by the definition of gamma function. So, this will be root pi upon 2. So, this particular integral is root pi upon 2. Similarly, we can solve it for any power of u, like u cube. So, if it is u cube, I will write u cube equals to t. So, then it will become 3 u square du equals to dt. From here du will be 1 by 3 u square dt and it will give me du equals to 1 by 3 u raised to power minus 2. So, u raised to power 3 u equals to t raised to power 1 upon 3. So, u raised to power minus 2 will become t raised to power minus 2 upon 3 dt. So, here I will write this integral as 1 by 3 and minus 2 by 3 can be written as 1 by 3 minus 1 e raised to power minus t dt. So, it will become 1 by 3 gamma 1 by 3. Similarly, e raised to power minus u raised to power 4 will become 1 by 4 into gamma 1 by 4 and so on. Let us take one more example. Solve the integral I equals to 0 to infinity 2 raised to power minus 9 x square dx. So, this is a bit difficult example if we see here, because what sort of substitution we can make here, but let us use the property of gamma function here. So, put, or before that I can write this as 0 to infinity e raised to power minus 9 x square into ln of 2. I can write this in this way into dx. Now, put 9 x square ln 2 equals to t. So, what I will be having, x square will be t upon 9 into ln 2 and 2x dx will become 1 upon 9 ln 2 dt, or simply dx will be 1 upon 9 ln 2 into 1 upon 2x. So, 1 upon 2x we need to find out from here what it can be, and then after putting here it will come in the standard form of gamma function, and from there we can write I equals to 1 upon 6 square root ln 2 0 to infinity t raised to power minus half e raised to power minus t dt. So, this integral can be written in this form, and you know it is gamma half. So, root pi upon 6 square root ln 2 will be the value of this integral. So, with this example I will end this lecture. So, in this lecture we have seen few definitions of gamma function. We have seen the value of gamma 1, how can we write gamma x plus 1 in terms of gamma x, and then we have seen how can we define gamma function for negative non-integer values. Finally, we have taken few examples and we have solved them, means examples of definite integrals, improper integrals, and we have solved them using the definition of gamma function. Thank you very much.